This is the second video for homework help for Chapter 7 in Statistics. In this video, we'll look at finding confidence intervals. Okay, so here's a big jump between the central limit theorem and confidence intervals. Now, all those means, all those distributions turned into bell-shaped curves with enough samples. That's what we had in the first lecture. Let's recall again these areas under the curve. You remember those from, I don't know, all the way through this class. So here's your bell-shaped curve, and this is the mean right here. And you know that between here and here, between plus and minus 1 standard deviation, lies 68% of the values. If you go plus or minus 2 standard deviations, you have 95.4% of the values, and then I'm not going to draw the other one. Plus or minus 3 is 99.7% of the values. Okay, that's how much is under that curve. So the area under the curve, let's just go plus or minus 1 standard deviation. That's 60% of the values. Here's the big leap. We say that if you go plus or minus 1 standard deviation about any, this is about the mean, any sample mean, any mean for any sample, plus or minus 1 standard deviation, okay, of the population, then you will have 68% confidence that the real mean lies in that interval. Okay, so we're taking the numbers off the area underneath the curve. Those give us our confidence levels. Confidence level is in percent, 68% confident. Here, if you want 95.4% confidence, you would have to take your sample average and you would have to go plus and minus 2 standard deviations. And that interval, constructed from that, will give you the confidence interval associated with a 95.4% confidence. Now with a bell-shaped curve, you aren't stuck to just having the areas that you know already. You can use any area you want. And there's a certain notation associated with it, and it's called Z. Okay, it's right here. Z, and the subscript is alpha over 2. Here's the idea. What is alpha? If you want a 90% confidence, as shown here, then that would relate to the unshaded area here would be 90% of all the values. Okay? So how much is rejected? 1 minus 0.9, or 10% of the values. We'll write as 0.10 instead of 10% and write it in decimal. These are the numbers that are rejected. And the parts that are rejected are in what are called the tails. Here's a right tail and here's a left tail. Since the total area rejected is 10%, then half of that is rejected in each tail. So the right rejected tail has a 5% area underneath it, and the left rejected tail has a 5% area underneath it also. And if you go to the tables, you will find the Z value associated with it. So that's the notation. Z alpha over 2 is right at the edge of the right rejected tail. Because the bell-shaped curve is symmetric, this value over here is negative 1.65. Okay, let me say that again. We're equating confidence intervals and confidence level to areas under the curve. When you look at the area under the curve, you'll have a certain amount of area that you're including. For example, 90%, because you want to be 90% confident. Well, if you have 90% of the area under the curve included, then 10% got rejected. The rejected is divided between 2 tails. So in this case, you have 5% out here and 5% here. What you need to find is the value, the Z value, right at the edge. The Z at the edge is called Z alpha over 2 because you've divided that rejected area by 2. This is how those Z values are used. If you remember, we were trying to find the interval about a sample average that we're saying includes, with a certain confidence, that includes the mean for the entire population. So here's the number I'm looking for. This is a sample mean that I measured on my samples that I took, any of the samples. I find the distribution standard deviation. I put that here. Now, how many of those sigmas do I move in order to include that different area? That's given by the alpha over 2. Remember, to include 68%, it only took 1 standard deviation. In that case, z alpha over 2 was 1. So this interval would look like this. And then be a 1 here. I'll put it in just for reference. The standard deviation for the distribution. And I would say with 68% confidence that the population mean is 1 is within this interval. Often you rewrite, instead of writing the standard deviation, this standard deviation, here you use one for the entire population, so you use this equation to rewrite it. Remember, z alpha is the value of z right at the edge of the rejected tails. And that's what you put in this equation. Now, there's some problems in the book where you have to go and find the z alpha for some strange numbers. Instead, I give you all those values. So hopefully you kind of understand that equation, because you're going to have to plug into it. So here's a table. It's there's one using this sigma in the lecture on easy confidence intervals. This particular table is in the one for sample problem, in the lecture for sample problems. So there are certain confidence intervals, the 68%, the 95.4%, and the 99.7% confidence levels all come from those areas under the bell-shaped curve that you know very well. In that case, you go 1, 2, or 3 standard deviations away. And so you see, here would be the z alpha over 2. Let me put that in a different color. It goes right here. In this case, it's 1, so it doesn't show up. Here it's 2, and here it's 3. This just has to do with those areas under the bell-shaped curve. Now, people don't generally talk in terms of 86 or 68% or 99.7%. You like to talk in round numbers, and typical ones are 90% confident, 95% confident, or 99% confident. In that case, you could go to the bell-shaped curve, find the alpha, and then go to the tables in the back of the book and find the z-value. However, they're fairly standard, and I've just written them down for you. If you want to have a 90% confidence level, you have to go 1.65 standard deviations away from the average. For 95% confidence, it's 1.96. For 99% confidence, it's 2.58. That makes sense, because to get 99.7, you have to go 3. Right? The more confident you want, the bigger the interval. If you have a real small interval, you're not so sure, the confidence level drops. So we start here with the homework, looking at z alpha over 2. What is alpha, and why is it divided by 2? Alpha is the area under the bell-shaped curve that's being rejected. And you divide it by 2 because that rejected area appears in the two tails. So on this curve below, shade the areas for z alpha over 2 is 1.5. Well, here will be your 1.5, right? You can do a better job than that, I'm sure. And negative 1.5 is right here. And these are the shaded areas. These are the values you're excluding. You're only looking here between this, and that would be this would be your confidence level, and here are the rejected tails. Now you get to write the equation for the confidence intervals of the population mean in terms of the z alpha over 2, the sample mean, and the standard error. Well, minus, and then z alpha over 2 says how many standard deviations you're going away. I'll just put d, and that's less than the mean. And so the mean is sort of captured between, the mean is captured between these two values with a certain confidence level. Now, if you want to write this in terms of the standard deviation for the population, then you replace the sigma distribution with sigma divided by the square root of n.